Okay. This is the equation we want to solve, and I want to do a simple massaging where I remove the just like before. I remove the unit of length because I want it to manifestedly looking like this is energy times u. This is also energy times u, and the way to do it is consider the a length scale just like in harmonic oscillator problem. H cut square by m square. This thing is also called the Bohr radius because it's the radius of the smallest atomic orbital, and replace r as a naught x in this equation. So when I do that, this equation comes to be of the form where I want to use one more shorthand, and the shorthand is minus 1 by x kappa. Okay, I missed one thing. This will be kappa u, or to be more precise, this is minus kappa square u, where kappa is minus e. So when I take out this a naught x unit here, it will go this side. So I can compress this to a notation 2z e square by a naught. Okay. So check that. This simple transformation just to bring the equation in a much more cleaner form. So we'll work with this equation. Okay. Okay, this is just variable transformation. So now let's try to play the same game as before, where we want to see what is the solution in various limits. And as we know, there are two important limits. One is x going to infinity, another is x going to 0. So let's first look at x going to infinity limit. So x going to limit, this is okay, because x going to infinity, I can throw away these two terms. So it is just a simple second order differential equation, which will have a exponential solution for a bound state. So bound state means kappa is negative. So this will have u e to the power plus minus kappa x. So kappa is unit free. It's a unit free quantity. Okay. And so I can rewrite a new length unit as rho equal to kappa x. So u is just e to the power minus rho. This is just a convenient choice, which I'll do one further transformation and write everything in terms of rho from now onwards. Okay. So now I got the x going to infinity limit solution. So now this equation in terms of this rho is now d2 d rho 2 plus n into n plus 1 by rho square minus 1 by kappa rho u equal to minus u. Okay. Just let me check one thing. D2 rho. Yeah, correct. Okay. So everybody is following that. What are the steps? I'm just not doing all these simple transformations. This was my starting equation. I redefined my r as a naught x, where a naught is some unit of length, some object of dimension length. As I told you, what is this a naught? And the reason to choose this is the length scale of the problem defined in terms of all fundamental constants and mass, which are given a priori in the problem. Actually, mass is also fundamental constant because it's electron mass. So everything is given as a natural constant, and it has a dimension of length. So I can simply rescale my variables. This rescaling by calling a naught x as my so basically x is my new unit of length, new length definition, which is r by a naught. So I rescaled r by a naught as new definition of length. So then I convert this equation becomes this when I put this, do this transformation, and this equation in the x going to infinity limit becomes simply this equation, which you have solved before. The solution is simply e to the power plus minus kappa x. Yeah, I missed this. There's kappa square. Solution is simply e to the power plus minus kappa x, and then I redefine again because this is just this kappa x. I just called it rho. Another, I redefine the unit of length again, and then my solution simply looks like e plus minus rho, and then I rewrite my x differential equation in terms of rho. Then it looks like this. Just a cleaning process where I make everything unit free. Okay, just like everything we did before. Now what I do here normally, that from here we have done this exercise before. Here from here we try to do a series solution. But notice this equation is not yet ready to have a series solution. Why? Because this has a second derivative. Second derivative means it will be a polynomial of 2 order less, of 2 order less. This is divided by rho square, so these two terms will be similar. But then it is 1 order less, just 1 order less, and then there is no, it's the same order of the full polynomial. So that was not the case before. Earlier, all the differential equations we got, when we started doing series solution, we had only relation between 2 orders of the polynomial, 2 orders of coefficient. Here we have 3 different orders. One is 2 order down, one is 1 order down, another is of the same order. So so from here we cannot you play the series solution game, so we have to massage it a little more. Unfortunately, we can do that by thinking of the other limit. So this one was x going to infinity limit or rho going to infinity limit. So this one was rho going to infinity limit. So this is not yet ready for series solution. I hope by now you are all well versed in series solution in math methods, right? Did you learn series solution in math? You are not taking math methods course, right? Okay, others in the audience?
Yes, sir.
Oh, very good. So then by now you must have practiced many equation and many differential we have solved. So you know that these, because of three types of coefficients, I cannot directly apply series solution. So what we will do is we will do one more level of approximation. Not approximation, one more asymptotic. We look at one more asymptotic side. Now rho going to 0 limit, what happens in rho going to 0 limit is that this term is the main term, okay? Everything else falls up, right? So this term, so the equation will be effectively d2 d rho 2 minus d2 d rho 2 plus L into L plus 1 by rho square, u equal to 0. So in that limit, of course, is a polynomial solution which has to be of the form u goes as rho to the power L plus 1. Then you take 2 derivative, it becomes L into L plus 1 with 2 powers of rho at the below. So that's how this satisfy this relation. So we got rho going to infinity, which was u go to minus rho, and rho, of course, it has to be minus rho. Here also minus rho, because otherwise it will blow up. So we got the equation solution in this 2 extreme limit. So that means my full u can be written in this form. Rho going to L plus 1. Its job is to give me the. Oh, I think I am not recording. Can you start the? Oh, you started. Okay, thank you. Okay, because I got some message that recording is complete, so I thought something I started and didn't close. Okay, so rho to the power L plus 1, W rho e to the power minus rho. So this is my answered solution. I know this is going to be there because of the rho going to 0 limit. I know this is going to be there because the rho going to infinity limit, and the rest I don't know what is in between. So that's why there is a W rho. So now I should be able to plug this in and get an equation in terms of W. That is my only unknown rho. So when I do that, the equation I get is as following. rho W double prime plus 2 into L plus 1 minus rho W prime plus 1 by kappa minus 2 into L plus 1. Okay. So when I plug this into this, I get a differential equation in terms of W. This is the differential equation. Now this is ready for series solution. Okay. Why? Because you can see that there are only two kind of powers involved. One is rho times double derivative, which is one power down from the full polynomial form. This is rho times W prime, which means it's a full W, and this is one power down. This is again full W. So it is relation between two coefficients. Earlier it had three coefficients involved in one equation. Now it is two coefficients. So now I can plug in.
Sir, can you rewrite that equation? It's not visible properly.
What is not visible?
The last equation you wrote.
The W equation.
Yeah, a bit bigger. Would be helpful.
Is it not visible because of size or something else?
When the how do you say it's a bit blurry. That's the problem.
Bloody. Okay, bloody is not. I cannot fix. So what about? Is it bloody to you? Okay, I can see it from here. So probably it's a connectivity problem. But it is a bit strange. You can see all other equation, but not this equation, right?
The part in the middle is actually pretty clear, but the more like the sides are a bit blurry. Can you just write it bit bigger?
Extra bright.
Okay.
Bloody due to the brightness.
So I can see it in my screen very well. So that's a
Sir,
surprising
it's
part.
like the lights are adequate for the middle part, but not the
Okay,
corner.
light reflection. Anyway, don't bother too much. The details doesn't matter right now. I will give you the notes anyway. If you understand the method by missing a factor of 2 or L, it won't be a big deal. L plus 1 minus rho W prime okay. So now I can admit a series solution which is k rho to the power k equal to 0 to infinity. So this is my series solution form. Now also see, as I told you earlier, there are only two powers involved. So I can plug this in into this, and this will give me a recursion relation of this form. As I can clearly see, there is only a relation between two order terms, which are one order higher and the same order. So it will be a relation between ak plus 1 and ak, and it will become this is a little tricky here because I have a kappa and k both, but since I am already using this notation, let me just stick with it. So this is kappa, this is k. The denominator is all k plus 2l plus 2. So this is my form, and as you know already that this series must truncate somewhere in order to have a normalizable solution for bound state. So that means there must be a particular for normalizable solution. Which means there is definitely a n plus 1 which is 0, and that is given by when this thing goes to 0. So that is 1 by kappa 2 n plus l plus 1. For k equal to capital N, that is, let's say for a particular capital N integer, let's say this condition is satisfied, then this must be the case for that. Yes. Yeah, that is kappa square. Okay. Yeah, you are correct. So this has to be kappa square. Let me just check. Yeah, this has to be kappa square. Correct. Very good. Okay. So okay. So this is my truncation condition, and the truncation condition tells me that, let me call these things. So this is an integer, right? This is definitely an integer. This is definitely an integer because n is an integer, l is an integer, because that is how we know that l is an integer from here, and 1 is of course an integer. So this I can rewrite it as some integer n plus l plus 1 by 2 kappa. Right? This integer, this has a name which comes from spectroscopy. It's called principal quantum number. So I am writing the equation in a form such that it matches with the spectroscopic notation, and when I do that, this integer is identified as the principal quantum number, and it is an integer, so it can have any values. So n can be anything. N can be 0, 1, 2, 3, and L can be 0, 1, 2, 3. That means n can be 1, 2, 3 because there is a plus 1. So these are the allowed values of n. So that implies that my E is, so now I go back to the kappa notation. E is minus 2z E square by A naught kappa square, which is nothing but, now k is, kappa is quantized, so this is En minus z square E square by 2a0 1 by n square. Okay. Now if you put actually the numbers and put it in a unit, this thing is minus 13.6 by n square in electron volt. Okay. So this is the famous result of hydrogen atom spectrum, the hydrogen atom energy levels, which was precisely verified by experiment. And what we got, starting from the basic Schrodinger equation, we derived this. Okay. So now let's go to the wave functions. Any questions up to this point? Okay, good. So let's go to the wave function. So what we got, starting from the Schrodinger equation of hydrogen atom, we got the energy level to be minus 13.6 n square electron volt, such that I don't have to remember all these complicated factors in the front. We write it in this way. And now let's go for the wave function. This is a little nasty because it's all this polynomial, all this complicated polynomial. So the polynomial that comes here is known as associated polynomial. Okay. Now, as you know, earlier also we have seen the associated legend that when the L is 0, then this differential equation, you get some special function, and then you bring back the L, then you get this associated forms. Okay. So Legout polynomial is nothing but when you solve this series equation without the L, and when you bring back the L, it's just the associated Legout. Okay. So this defines as, there is not much point of writing this. This is just a complicated equation. This defines as minus 1 to the power k. This is k, not kappa. Minus 1 to the power k dk dxk lp plus k0, where lp plus k is the regular Legout polynomial, and this is the associated one. So L rho 0, no, not p, this is rho. No, this is p, sorry. This is also p. So LP0 is basically e to the power x dp dxp. There is no point of noting this down. I'll give you note and it's there in the book, and nobody's going to ask you to remember all these things. Just know that the structure is there. So, but it's admirable that somebody have worked it out. So just that we don't have to. So this whole thing is written in a shorter form as this whole polynomial equation. It is 2l plus 1 n minus l plus 1 rho. So notice that these polynomials are of order capital N. Okay? So capital N is the truncation criteria. So they are given by N, and N is N minus L minus 1. So that's why I have written it in this form. So if I write down the full form, so then my psi. So I started with the U equation. Remember, I started with the U equation. The actual equation is U by R, the psi. So then it is so I just discussed this R part. So there will be of course a theta phi part, which are the spherical harmonics. And if I write it in full form, it becomes n rho to the power L plus 1. If I write everything in rho notation, divided by rho W n L rho e to the power minus rho phi lm theta phi. So this is my full solution, and this thing. So let me rewrite it. Let me get rid of this one here, and this is a polynomial of degree n, which is n minus L minus 1. Okay, this polynomial. Okay, so let's look at some of the wave function. Polynomial in R. Okay, let me share with this hyperphysics page where this is very nicely written. Can you see my tablet screen?
Yes, sir.
Okay, I just googled hydrogen atom wave function just to show you these mathematical forms. This hyperphysics page is very useful. So I have defined an hydrogen atom wave function in terms of this n, L, and m. Okay, and this is nothing but, if I look at the page, so this is the phi part. So the table can be read as follows: n, L, m can have all these possible values as you have seen, and I'll come back to once more to discuss what are the allowed values of n, L, m. But let's just look at the table, and there is a phi part, there is a theta part, and then there is a R part. When I write all of them, this is how it looks like, and they have a formal name in chemistry. They are called 1s, 2s, 2p, all these 1s or 2p orbital that you have learned in various chemistry or various some other courses before. And this is just the functional form of this. So the point to note is they are generally a polynomial times e to the power minus R function, which is of course evident from the form we wrote down. So this is the full form. So these are some higher order terms, just more and more complicated. Okay, these are just more higher and higher order terms, and so on. Okay, now if we want, you can see the pictures also. So let me see, where is the picture? Yeah, so this is a this picture. If you look at Wikipedia, this is the wave function form for various orbital, but they are 3D, of course. So what you have to do, you have to plot the r space and multiply it by theta and phi, rotate it by theta and phi. So this is a particular cut of that 3D projection of the 3D wave function. So this is the XZ plane cut, and that is how it looks like. So there are actually better picture of the 3D also. So let me see 3D. 3D images. There is not very good pictures. Yeah, okay, here are some pictures. Yeah, so this is some of the pictures which you might have seen before. So it's easy to see that when the L and M are both 0, then it will be, there is no shape in the theta phi direction. They are all uniform in all directions, so it must be a sphere. And when L and M are not 0, then of course you can have some more peculiar structures, because now the theta phi has a different spatial dependence. So let me see if there is. Usually these chemistry web pages have very good pictures, but I don't see them. Yeah, anyway, just Google this. This is not nothing very difficult to find. Let me try it once if I see it here. This is a chemistry page. They should have it. Okay, they have all the wave function forms, the mathematical form, and they have the radial part. They have just plotted the radial part of this. Here, very nice. So so this is the 1s orbital. As you can see that they have just drawn it in a way that it looks like they have cut the sphere. So 1s, 2s, and 3s, they are all spherical because they are just s, which means L and M are all 0. And then there is this px, py, and pz, and d, and so on. Okay, so on and so forth. So there is nothing very profound here. Okay, so let me go back to the go back to the Blackboard teaching and tell you that what are the allowed values of n, L, and M. So psi 1, 0, 0. If I put these things and use the normalization, it is pi n naught q. This is the s orbital 1s. Similarly, 2s is nothing but 1 by 32 pi a naught cube 2 minus r by a naught or minus r by a naught psi 210 psi 21 plus minus 1. Similarly, you can write them as this same factor times r by a naught e to the power minus r by a naught cos theta, which comes because of the L part. There is no M, so there is no phi. Phi is e to the power im phi, if you remember. So this is nothing but some factor. Let me not write it. R by a naught e to the power minus 2r by a naught s theta e to the power plus minus I phi. The phi is nothing but e to the power m phi, and so on. You can write these equations, and you can easily make the picture by drawing the r one-dimensional r space or one-dimensional plot and rotating him by theta in one direction by that c theta factor and phi by the phi factor. Okay, so let me say a few words about the allowed values, which is kind of important, and you learned it. All these things were discovered empirically in the context of spectroscopy, but now we are doing all these things formally. And the beautiful thing is that the formalism is so good; it precisely gives you the what you expect from experiments, or what you know from what you know from experiments is hard to say what you expect. So, number of states, which is n. Also notice once more that this is not a polynomial of order this n, which is normally the way we set up in one-dimensional problem. It's whatever identifies the energy eigenvalues, the integer, the polynomial is of same order. Okay, that has to be, because that tells you, that comes from node theorem. How many times it cuts the zero, that tells you how many roots the polynomial must have. That will be the order. But in this case, the polynomial is order n. Why? Because I have taken a polynomial part here already, which is of the form rho to the power l plus 1 divided by rho. So to match this, so this u polynomial form, the whole thing, it has to be of order capital N, which is n minus l minus 1. That is the difference from 3D problem. It is just a matter of convention how we set up the thing. So the number of states n, l, m and total. So if n is 1, n is 1 means, notice what is the n? N is this. So n and l, they both have to be 0. M also has to be 0. Also the m doesn't feature here, but we have earlier seen that m is bounded by l. Okay, m was bounded by, mod m was bounded by l. Okay, so if l is 0, m has to be 0. In order for the polynomial to survive, in order for the angular part to survive, this has to be satisfied. So l is 0, so m is 0. So if it is 2, then l can be 0 or 1. So that means m can be 0 plus 1, 0 minus 1, because it's a mod. So there is total one state of this. The entire, also notice, the entire energy is specified by this n, because the energy is of the form 1 by n square. So these numbers, they specify the wave function, but they don't feature in the energy. So that means whatever values they can have, this is all a degeneracy. Same energy, the energy is given by E1, this is E2, which is minus 13.6 EV, which is minus 13.6 by 2 square EV. Okay, this is totally specified by this, but this is this as, there is one state, there are 4 states of same energy. Similarly, 3 can be 0, 1 and 2, and this can be 0, this can be minus 1, 0, plus 1, this can be minus 2, minus 1, 0, plus 1, plus 2. This is the s orbital, this we know as s, this is the p, this is the d, and so on. Okay, this has a degeneracy 9, and you can actually calculate the degeneracy is 2l plus 1, which is obvious from here. This is the degeneracy. And if you sum the total number of states, so if you sum of n equal to 0 to l equal to 0 to n minus 1, you will get n squared, which is what you expect. Okay, so this is basically the full picture, and yeah, so that is all I wanted to show here. Okay, any questions here? Now I will switch gear and move on to a different topic. All super clear, very good. Okay, yes, which sum? You don't know how to do this sum? Sorry? Yeah, L has to go to up to n minus 1, right? Because n is given by, if n is 0, L must be n minus 1, then only it is 1, right? That is the minimum. So that's why it goes to 0 to n minus 1. Okay, so now I will move on to a different topic, that is more formal discussion of this rotational symmetry. And that's where I will come across this question that was asked, that how to think about the cardinality of Hilbert space. Okay, so let me talk a little bit about the question. The question is very interesting and very nice to discuss. So the question was, I think Shayantan asked this question, that if I measure, for example, energy, that's a discrete quantum, and if I measure position, that's a continuum of infinity. So what is the actual dimension of the Hilbert space? So this question is hidden, the answer to this question is hidden in Stern-Gerlach again, where again, that's where I always say, keep thinking about Stern-Gerlach all the time. Now, if these two observables are not commuting, which is just like classical mechanics, then this is not a puzzle at all, because they are two completely different observable, which has no reason to be connected. It is like, say, if I ask what is the weight of a person and what is the handedness, the person is left-handed or right-handed. So there are infinitely possible answer for the weight, because it's a real number, and the left-handed, right-handed has only two answers, and they are completely independent, just like this Stern-Gerlach experiment with balls we did, right? It can be either of a particular color or particular hardness or shape. Okay, so then that is not a problem. So if there are two observables that are not commuting, okay, they are not commuting, so they are two completely separate observables, they can have any values. But the problem is, if they are commuting, okay, if they are commuting, then what to do? And then it's a difficult question, because now I am saying they must have a shared eigenspace. Okay, their eigenvectors are common, and then I'm asking, okay, my electrons have a x, y, z, or r theta phi, whatever I like to call it. So if I measure the position, I'll find it anywhere in this space. But if I measure spin, I will find either up or down. So one is a two-dimensional Hilbert space, another is an infinite dimensional Hilbert space of the same eigenvector, because they share the eigenvector. If I think of spin and position, they share, or spin and energy, they also share. Right? Then there are n possible. NLM is the space of discrete space, and spin has only two quantum number, which is m and s, which is +1 and -1, or up and down. Okay, so we'll see how to make sense of this. Okay, it's a question, and one more thing to remember. This has to do with the this fact that what is the dimension of a Hilbert space of a problem, it depends on what are you measuring. Okay, this is again going back to the basic philosophy of quantum mechanics, that there is no point of talking about a property or of a object unless it is associated with a measurement. So a measurement produces the property. Therefore, if you are measuring spin, it's a two-dimensional Hilbert space. If you are measuring position, then it's an infinite dimensional Hilbert space. So turns out the answer to this question, how do you think about this? This is a x, y, and z. Okay. So you can think this as a multi-component wave function. So this is the plus component, this is the minus component. So this is the multi-component wave function. This is a 2 by 1 Hamiltonian, 2 by 1 wave function. And each of these components is infinite dimensional. So it's an infinite dimensional object. So psi plus is one position, psi plus another position, and so on. Then psi minus one position, psi minus another position, like that. So this is an infinite dimensional 2 times infinity, because each of them are infinity, represented in a complex form like this. So now if you apply a spin operator, how do you operate a spin operator? I say it's sigma z. Okay, so sigma z is 1 minus 1. But when I say sigma z here, it means 1, 1, 1, 1, 1, and minus 1, minus 1, minus 1. So this has a shorthand notation. It's identity. This is minus identity in this n by n space, and this is 0 and 0. Okay. So now if I operate this, then I get h bar by 2 plus minus h bar by 2 depending on this. So this is the way to do it. And if you have, I believe you have learned direct products, which you told me earlier that you have learned. So the full wave function in bracket notation is direct product of these two spaces. In other words, like a Cartesian product of these two spaces. So let's do it more formally. Okay. So are you now kind of satisfied with the answer, that how you can have this, how you can deal with these two different aspects, two different cardinality in one form.
Yes, sir. I was just thinking that a vector space can only have some specific dimension. It can have multiple dimensions. That's why I asked the question. I kind
Yeah,
of
so
understood.
this is how you handle this
Okay, sir.
this thing. Okay. Okay, so it's a tricky question for when they are commuting observable, because they must have the same eigenvector. If they are not same, then it is not a problem. Okay, so now let's talk about this rotation a little more formally, because notice when you studied in chemistry or anywhere else, you studied that there are four quantum numbers: n, l, m, and ms. Okay, so psi was n, l, m, and ms. This was called the principal or the, no, not principal quantum number. This has some name, some main quantum number. This was azimuthal, and this was magnetic. Why it is magnetic, that you will understand in quantum mechanics too. You will see that if you put a magnetic field, it splits because of that part. And then there was a spin. So far I avoided the discussion of spin. So it turns out the spin has to be brought in quantum mechanics without, if you are not in a relativistic domain, you have to bring it by hand as an empirical fact and interpret it from the structure of a function. You know that there is spin, so you want to develop your formalism according to that. But if you do relativistic quantum mechanics, which is what we will do in Dirac equation near the end of next semester, quantum mechanics 2, then you will see you don't have to bring it by hand. It emerges from the theory. The theory demands, because it has to satisfy relativity. Okay. Okay. So the idea is of multi-component wave function. So psi. So if you're thinking of z, you know there are two parts. One is plus z psi. One is minus z psi. Okay. So this is like plus z psi plus minus z psi minus. So this in the position form is, so this is a notion of two component wave function. And in a formal language, you write it as the full wave function must be described by, there is a position and there is a spin. Okay. So altogether, this is just x, y, z given by sigma. This is a two-dimensional space, this is an infinite dimensional space. So now what is the physical meaning of this multi-component wave function? This is we already discussed, because we know classically this two-component wave function or two-component objects, you cannot describe it by a single component, or this what are these things called? I'm forgetting. Classical version of spinor, the gimbals, this thing I showed you, that you cannot rotate it by 360 degree, it will not come back. You have to rotate it by 720 degree. So let's say I want to describe the notation of such a thing. So you have learned rotation extensively for rigid body, because rigid body rotation is very simple. The idea is I have a point at xyz, and it is going to some x prime, y prime, z prime by some theta. So this is the object, it goes here, and you can get the full form. But if it has a structure, let's say it is a vector called psi, and when you rotate, this vector also rotates. So this vector, let's say, also rotates. So it is not just transporting this object here. If you transport this object here, it will be something like this, but it also rotates itself. So there is a rotation in that, it's not a rigid body anymore. It has a rotation in its own internal dimension, in own internal space. So when that happens, you need a multi-component description in classical dynamics. Okay? Generally, you have not done rigid body, so you will not. I will not go into that non-rigid body. So this is in wave function language. Wave function is a vector in Hilbert space. It has, let's say, multi-component. So it has a rotation of its coordinate, but it also has a rotation in this space, the sigma prime. So how do I handle that? How do I handle this full thing? So in other words, you can describe, if I do a r psi x, r is some operation. If it is a single component, you can simply get it by doing psi r inverse x. You can write it also as rx if you are thinking of passive rotation or active rotation. I am writing it in the form of passive rotation. That means instead of rotating the object, I rotate the coordinate. Okay, that's the passive rotation. But if it is multi-component, then an r acting on psi x will have two things. One is, of course, psi will go to r inverse x, but also there will be a dr acting on this whole thing. So I want to find the what is the form of this dr that takes you this sigma to sigma prime. I know what to do with the rotation part, and we want to find this full form that takes you from one abstract vector to another under the action of rotation. So we want to find a formal description of this thing, and as you know that since this is the alpha r, as you know that rotation is a continuous transformation, which means it must have a Lie algebra description. Now if it has a Lie algebra description, you should be able to describe everything about rotation in terms of its generator. Okay. So what we will see, we'll describe this full formalism of rotation in terms of the generators of rotation, and that is what we'll do next time. There is no point of starting this new chapter now. So meanwhile, you just internalize the hydrogen atom, and this is just a prelude of what are we going to do to describe in general rotation of a multi-component wave function. Right? That is what we'll do next. Okay. Also, single component will be a special case of multi-component, of course. Yes. Yeah. All I'm saying is, so let's say I have an object which is not a rigid object. So when you rotate, the object just doesn't go like this. It also rotates in its own plane. Okay. So you can think of a object with a hinge. Okay. This selfie stick, let's say. So when let's say you are rotating this object. So versus when you are rotating just a rod. So when you rotate the rod, you know the rod will be just this. But when you are rotating this, let's say it also rotates in its own plane. So to describe such a thing, you need something, you have to describe both of these, the rotation of the whole object and the rotation in its own plane. So that is the classical equivalent of spinors, multi-component wave function. More hinges you have, more coordinate, more bigger dimension you need. So in quantum mechanics, we will not go to the classical version. Of course, classical you are expected to learn elsewhere. So I'm just giving an analogy for you to understand this is not a super strange thing. It's normal. It happens. What is strange that how come electron is that? So that is the peculiar part. Electron is a point mass. How come it does that? So that for that you need QED and all that. But what we will try to understand, we'll assume electron is such a multi-component object. And we will we'll find out what is the form of this dr. What is the property of this dr that tells you how to take a wave function from here to here under rotation. That is what we'll learn. That is the next lecture. Okay, questions? That's all for today. Good. If none, I'll see you tomorrow.